Hello everyone, welcome to Tan45 Engineering. We are here with yet another video in our Mastering Data Structures and Algorithms in Java. Today's topic is insertion sort. So let's get started. So on insertion sort, again it's a very simple comparison based sorting algorithm, just like bubble sort and selection sort. It's efficient for small data sets and mostly useful when the data set is already partially sorted. So unlike selection sort, if the input is already sorted, insertion sort will not perform its operations. The algorithm builds the sorted array or list one item at a time. It takes one element from the unsorted portion of the array and places it in the correct position within the sorted portion. Okay. So we'll take a quick example for the input 12, 11, 13, 5 and 6. Okay. So before I go on into insertion sort, imagine it like this. The easiest way to remember is insertion sort is actually our go-to nature. So when you have a deck of card in your hands, what you do is you pick a element. Let's say you pick 5. You already know that 5 is smaller than all these cards. You directly put 5 in the beginning of this. Then you pick a 6. You insert it in the middle of 5 and 12. Hence insertion sort. And similarly you do with the rest of the numbers. So if they are already sorted, you wouldn't pick any card out of this, so you would not perform your sorting. Okay, so let's go next. So how insertion sort works. Okay, so we'll go through step by step and let's see. We have 5 steps. Let's see we solve the problem or not. So start with the second element in the array, considering the first element as a sorted portion. Okay, so we'll consider that this side is already sorted. First, if let's say there is only one element 12, it is sorted, right? It's a single element. So we have already considered that 12 is sorted. So we'll start with 11, the second element. So we'll start from here. Okay, start with the second element in the array, considering the first element as a sorted portion. Okay, compare the current element key, that is the second element, with elements in the sorted portion. Okay, so we will call this as key. Okay, so we'll say key is equal to 11. We'll compare this with the sorted portion, that is 12 on this side. So 12 is actually bigger than 11, right? Shift all elements in the sorted portion that are greater than the key to the right by one position. Okay, so it says all the elements on the sorted portion, this is sorted portion, we'll compare them with the key, that is 11, and if they are bigger than the key, we'll move them up by one position. So 12 will go to this position. So the next it will become 12 is here only, then 12, 13, 5, 6. Don't worry, we have the key here. Okay, so we have moved all the sorted elements to the we have moved them by one position up. Okay, so since there was only one element 12, it has been moved to 11th position. So I'll mention the indexes as well: 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Okay, so 0th position 12 has been moved to first position. Okay, we'll go back not this way. Yeah, shift all elements in the sorted portion that are greater than the key to the right by one portion. Insert the key into its correct position. Okay, so now we have the key, that is 11. We need to insert it into its correct position, that is here. So it will get changed to, key will get inserted here, 11, 12, 13, 5, 6. Okay, then let's see what happens next. Repeat the process for all elements until the entire array is sorted. Okay, so as of now, earlier we had considered that 12 up till 12 we were sorted till 0th position. Now till we'll do I++ and we'll consider that up till here we are sorted. Okay, so this will be our key, this will be our key. So we can say key is equal to 13. So we'll do the comparison for all the elements before in the sorted side. This is the sorted side, and if any element is bigger than 13, we'll move that up by one space. So since we'll compare it with 12 is already smaller than 13, no movement. 11 is already smaller than 13, no movement. Okay, So after this pass also it will become 11, 12, 13, 5, 6, and up till here we are sorted. Okay, so next our key will be 5. This will be our key. So key is moving up by one space, so we can always keep let's say if we are starting from the first element, we'll directly give I is equal to 1, and we'll always say key is equal to array of I. And in our first for loop outside, we'll be doing I plus plus. So after each iteration the I is moving forward, that's why the key is changing. In this iteration key was at index 1, now here key was at index 2, and here key is at index 3. 0, 1, 2, 3, 4. So at index 3 key. Okay, we take the key. Now we compare all the elements from the sorted end one by one with 5, that is key. So we'll say key is equal to 5, and for all the elements that are bigger than the key, we'll move them by one space. So 13 is bigger, 13 will come to its position. 12 is bigger, 12 will also move to one position. 11 is bigger, 11 will also move by one position. So if I go them one by one, it will become in one pass, it will be 11, 12, 13, 13, 6, then it will be 11, 12, 12, 13, 6, and lastly it will be 11, 11, 12, 13, 6, right? We have moved all the elements up by one position. So 11 was at first position, now we can see it is at second. 12 was at second, now it's at third. 13 was third, now it's at fourth, right? And in the end, when this is done, we insert the key back to its correct position. So where will we insert the key? Let's insert always the key to the place up till where we could make the swaps. Okay, so we'll always remember that position by our inner loop, that will be J. We'll use J to keep track of the key's position. Okay, so now key will switch back and to its correct position, that will be here. So it will become 5, 11, 12, 13, and 6. Okay, now again we'll repeat the same process again with this one, but now up till here the array is sorted. Now we'll take 6, we'll start the comparison. 6 with 13, no movement. 6 with 12, no movement. 6 with 11, no movement. And 6 with 13, of course there is movement. 13 is bigger, 12 is bigger, 11 is bigger. So these three will shift forward, so it will become 5, 11, 11, 12, 13, 11, 12, 13 will come here. 1, 2, 3, 4, 5. Oh sorry, this is not there, no? Yeah, okay. So 11 moves to the next position, 12th position. 12 moves to next position, and then 13 moves to next position. Okay, and 6, so some of us might be assuming that 6 is lost, but no, every time we are storing this in a key variable, so 6 is here. In the end we insert 6 into its correct position. Now the correct position will be here, right? So it will become 5, 6, 11, 12, 13. That's all. I hope that's clear. Okay, let's go into the code and understand it on a better level. Okay, so we'll start here. Let's take the input. Int array is equal to 12, 13, 11, 11, 13, and then with 5 and 6. Okay, now we'll call our insertion sort. So insertion sort, pass the array, and then system.out.println sorted array. Now for int I is equal to 0, I is less than array.length I plus plus. We'll print system.out.println not ln print array of I plus some space. Okay, now we'll write our this is our main method. We'll create for sorting method as well. Too much space. Yeah, so we'll say public static void insertion sort, pass our array. Okay, now we'll first take the length, that is int n is equal to array dot length. again what else do we need? Let's start with the traversal. For int I is equal to 0, I is less than n, I plus plus. Okay, so we have the outer loop that is actually going to perform the traversal for all the keys one by one. So okay, we are starting from the first, not the 0th, right? So I will actually be equal to 1. Yeah, okay, I is equal to 1, I is less than n, I plus plus. So we start with this here, right here, the key is at 11. So we'll take the key, we'll say int key is equal to array of I, right? So I is at 1, array of I is 11, 11 is our key. Okay, now next would be another variable, int j is equal to I minus 1. Okay, so what we are going to do is, when we are making these movements, okay, like these movements, I'll take this one. Okay, in this case 5 is supposed to go back all the way, right? We have to move all these three elements. So how do we do the movement is, we keep a variable j here, okay, and we move j to j plus 1 again, and then j minus minus, then j to j plus 1, j minus minus, j to j plus 1, j minus minus, and then in the end j will be at a position where we will directly insert the key. Okay, let's go back. So j is equal to I minus 1. So for the first case, or we'll directly consider from here, j is at 13. Okay, then we'll say, okay, let's write it, shift all the elements, but which elements of array? There will be 0 to I, right? I minus 1, 0 to I minus 1 that are greater than key. Okay, to one position ahead of their current position. It's too long of a sentence. Okay, so we'll shift all the elements before this key which are greater than key by one position forward, right? And since this is already sorted, once we have moved all the elements that are greater than key, we don't have to compare for the back elements, since they of course would be smaller. Like in this case of 6, we compare 6 only up till 11, and after that, since 5 is already smaller than 6, we don't have to compare any elements if there are before 5 as well, since that would already be sorted. Okay, so for this we will say, while j is greater than equal to 0, okay, because, okay, I'll just simply write this line here for everyone. So we are at 5, 11, 12, 13, 6. Okay, up till here the array is sorted. This is our key, so we have key saved somewhere. Key is equal to 6. Then j is I minus 1, so at this stage j is pointing here. So we'll do the comparison and move them by one space, and for all the values from j starting from here all the way down till 0. Okay, so we'll say j is greater than equal to 0, and array of j, it should be greater than key. Okay, if this happens, we'll move the elements by one position. So we'll say array of j plus 1 is equal to array of j. Okay, so if you see, j is here at 0, 1, 2, 3, 4th index. So we are saying array of j plus 1 is equal to array of j. So j is 0, 1, 2, 3, j is equal to 3. So array of 4 is equal to array of 3. So this element will move here and it will get 13 here. Okay, now we move the element. After that, j is equal to j minus 1. Okay, so now once we have moved the element, 13 is moved to the next position, we'll reduce the value of j. So j will now point to lower index, that is 2. Again array of j plus 1, that is array of 3, will get the value of array of 2. So 12 will go to this position, similarly 11 will go to this position. 5 will not go, since it will break the loop that it is not greater than the key. Okay, but 5 will not go, but j will be residing here. Okay, so up till here it would have moved, and array would look something like this, that 5 6 11 12 13 13. Okay, but our key is still holding the value 6, and j is pointing here at sorry, this is not 6, this would be 11 to, this is not there, no? Yeah, 13 moved to 6th position, 12 to 13th, 11 to 12th. So 11th position is still 11. 11 is there, j is pointing here, key is 6. So in the end we can say array of j plus 1 is equal to key. So j is here, j plus 1 here is equal to key. We'll get the 6 here, and this will become 5 6 11 12 13. Okay, let's go back to the code. So j is equal to j minus 1, and in the end, once this is done, we'll say array of j plus 1 is equal to key. Okay, that's all. Let's run the code, and we can see 5 6 11 12 13. Okay, so that is majorly all. We'll cover some pros and cons, and the time complexity, space complexity. Time complexity, of course, O of n square. As you can see, the outer loop, that is dependent on n, value of n, and the inner loop, again it is dependent upon the value of n, because j we are checking greater than or equal to 0. J is already given the value of I, j is already getting the value from I is dependent upon n. So if the n is larger, j will get larger values, and the loop will increase based on the value of value of n. So both outer loop, inner loop are dependent upon n, and they are inside each other. It will be O of n cross O of n, O of n square. Okay, space complexity O of 1, because as you can see, apart from this key variable, we do not use any other data set for memory, so it's in memory sorting. So space complexity is O of 1. Pros: insertion sort is easy to understand and implement, and pretty straightforward. Insertion sort is adaptive. Yes, so unlike selection sort, insertion sort is adaptive. That means if the input is already sorted or partially sorted, it will give us the best case time complexity of O of n. Insertion sort can sort a list as it receives it, so this is a very good advantage. So it can sort the numbers as and when it is receiving. You do not always need to have the complete list of numbers. You can process them one by one, and you can still sort it. So this is useful in scenarios where data is received in a stream and needs to be sorted. Cons: of course, inefficient on large data sets due to its O of n square time complexity, and due to its inefficiency on large data set, insertion sort is rarely used in real world applications where performance is very critical. So all the sorting algorithm that are giving O of n square, they are very good for small data sets, since they are simple to implement as well. But for larger data sets, we go for more advanced sorting algorithms. So that's all from today's video, everyone. For anything, please let me know in the comment section. I'll be happy to answer. In the end, please like, share and subscribe. Thank you.